Hi everyone. In this video, we will learn about the other operation on a vector field, which is called divergence. So let's start off with the definition. If we have a vector field F with component vectors P, Q, and R, P, I cap, Q, J cap, and R, K cap, in R3, which is 3 space, and the partial derivatives del P, del X, del Q, del Y, and del R, del Z, that's the respective partials in their X, Y, and Z components, exist, then we define divergence of F as the sum of these things. So this is a scalar quantity. It is a scalar quantity, and once again, if you recall that del is an operator which gives us this vector associated with the directional derivatives here in x, y, and z direction respectively, then I can write this divergence as simply the dot product of the del operator and the vector field f, which sort of completes the circle in the sense that we had a cross product in defining curl, so it seems quite natural that the dot product would also have a special name and a special relation with what information it carries, and it is called the divergence of this vector field f. Calculation of the divergence is much simpler than curl because we don't have to deal with determinants. Divergence of vector field f is simply the dot product of f with the del operator, which means we take the x component, take the partial with respect to x, we take the y component, partial with respect to y, and we take the z component, partial with respect to z, and add them up. This is z, this is xz, and this is 0. So this is z common, 1 plus x. And that is the divergence of this vector field. Now we have a theorem which sort of connects curl and divergence, which says if we have a vector function f given by its components pi cap plus qj cap plus rk cap on R3 again, p, q, and r have continuous second order partial. We need the second order because we are doing two operations, which means we are taking partial twice, and the result is that the divergence of the curl of a vector field is always 0. And the proof of this is we can again expand, right? So divergence of curl of f is going to be written as del dot del cross f, and you can sort of already see that having this dot product here is going to, all right, so before we do the actual like written out proof, you can also consider, remember what cross products do, right? Since you're crossing del and f, the result is going to be perpendicular to both del and f. Then if you dot del with something that's perpendicular to del, you will get 0. So it makes sense that it would be 0. But we can write it out. So this is going to be del over del x, writing out the expanded form instead of the determinant, because I mean that makes it easier to see what's going on here. Del z minus del r del x, and something similar to what happened in that previous proof where we said that the conservative field, that is if you take the curl of a gradient field, it was 0. You will get a bunch of second order partials, but a lot of them will be similar and therefore get cancelled out. So if you take del z del x, a positive, a negative, del y del z, where's the del y del z, positive, negative, del y del x, negative, positive. So all of that cancels out and becomes 0. Note something here which you may be asked in your exams and stuff is consider other combinations, right? So wait, does divergence of f mean anything? Does curl of f mean anything? So this was divergence of curl of f. What about curl of divergence of f? Or what about curl of f and things like that? So sort of think about which of these makes sense first of all to ask, and also if it does make sense, is there something nice? Is what something zero like over here, or some other interesting things? So try it out. That will help you be a little more comfortable and familiar with using both curl and divergence notation. Similar to the idea of curl, we can ask why it is called divergence. And as you know, the meaning of the word divergent means it's something that's spreading out. Let's look at these two vector fields and specific points P1, P2, and P and see what's happening. So if I look around P1, the size of the arrows are changing. The size of the arrow coming in is a little longer than the size of the arrow leaving. Similarly, if I look at P2, the size of the arrow coming in is a little shorter than the size of the arrow going out. So these ones have divergence which are non-zero. Whereas over here, if I look in and around P, the size of the arrow more or less remains the same. So in this case, divergence F is 0. So what divergence does is it again in terms of fluid mechanics or study of fluids in physics and engineering, divergence is sort of like saying how much a certain fluid can be compressed. If the divergence is 0, it means it's incompressible. So all the vector fields are same length arrow everywhere. Whereas if it's non-zero, then it has certain amount of compressibility. It's a net rate of change of the mass of the fluid as it flows. And that's what gives us the divergence. Oh, wait, what's the space for? Anyways, we can... Okay, the next thing that occurs, if you do this little exercise over here, you will see that some of these make sense and some of these do not make sense. There's something called a Laplace operator, which incidentally happens to come out when you take the divergence of a gradient field. So basically this is del dot, already del of f. So this becomes a scalar quantity, second partial differential of f in each component, and all of these added together. And we have another notation for this. The notation for this can be written as del squared, which is basically del dot del. And this operator is called a Laplace operator, and we can think of this itself as a another operation. So if I have del squared of f as a vector field, it basically means del squared pi cap plus del squared q j cap plus del squared r k cap in each of the three directions. We will end this video here for divergence. So it's basically dot product. We just need to know what it would mean for something to have 0, why the divergence of the curl of a vector field will always be 0, and just be familiar that this del squared operator is called Laplace operator, which you will probably see in your other classes with physics and engineering. We'll stop here, and in the next video, which will be the last for this section, we will look at how we can rephrase what we had in Green's theorem, but written as vectors.